Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The legacy of Heike Kamerlingh Onnes and his Leder laboratory finds its most perplexing and profound articulation in the state of knowledge concerning superconductivity, as it was consolidated around the year 1927, while Onnes himself had passed away in 1926. The ongoing research program he initiated produced a body of evidence and a set of empirical laws so robust and so strange that they commanded the attention of the world's preeminent physicists at the Fifth Solvay Conference. This essay undertakes a critical evaluation of the central claims presented by the Leiden school in this period, treating this consolidated body of work as a single, posthumous testament to Onnes' foundational discovery. We shall proceed through a systematic analysis of the work's primary assertions, from the cryogenic techniques that enabled the discovery to the bewildering properties of the superconducting state itself, evaluating the internal logic, the experimental evidence, and the conceptual frameworks that defined this revolutionary chapter in physics. This examination will reveal a monumental achievement in experimental practice, one whose empirical solidity created a theoretical vacuum that would persist for decades, a testament to a phenomenon discovered far in advance of its explanation. Section 1. The pursuit of absolute zero and the liquefaction of helium, the foundational claim of the entire research program, rests upon the mastery of cryogenics, specifically the liquefaction of helium. In 1908, the Leiden laboratory's assertion was one of unprecedented access to a new physical regime, a domain of temperatures approaching absolute zero. Their method, a sophisticated cascade process culminating in the Hampson-Lind cycle with a Joule-Thomson expansion, was presented as a triumph of engineering and thermal management. An evaluation of their reports reveals an obsessive attention to thermal isolation, employing concentric vacuum-jacketed Dewar flasks, a technique Onnes perfected. The internal arguments for the validity of their temperature measurement relied on the helium gas thermometer, calibrated against the established international hydrogen scale down to its limits. For temperatures below 4.2 Kelvin, the boiling point of helium, they relied on relating the vapor pressure of the liquid helium to temperature. This claim of accurate thermometry in an uncharted regime was critical. The internal coherence of their work is impressive. They cross-validated their pressure at temperature scale against the thermodynamic consistency of other physical measurements. The genius of this foundational stage was its systematic, almost industrial, approach. Onnes built a cold factory, and the claims about its capabilities were supported by a meticulous, interlocking system of refrigeration, cycles and calibrated measurements that gave the international community confidence in the temperature values reported from Leiden, making the subsequent discoveries built upon this base credible from their inception. Section 2. The initial anomaly in the resistivity of mercury, the pivotal discovery, as detailed in reports from 1911 and consolidated in the later understanding, centered on the electrical resistance of a thread of exceptionally pure mercury. The central claim here is twofold: that the resistance dropped precipitously and that it fell to a value experimentally indistinguishable from zero. On this initial hypothesis, rooted in classical physics and Lord Kelvin's conjectures, was that the resistance of a pure metal would fall to a low, constant value as thermal vibrations of the crystal lattice ceased near absolute zero. His experimental data directly contradicted this. The Leiden group's argument for the validity of the discovery rested on the systematic elimination of experimental artifacts. They argued that the sudden drop, observed at approximately 4.2 Kelvin, was too sharp to be an instrumentation failure. To counter the possibility of a simple short circuit in their cryostat wiring, they repeatedly redesigned the sample holder. Demonstrating the reproducibility of the effect, the core of their claim was the sheer magnitude of the change. The resistance failed to simply decrease, it underwent a phase transition into a new state. Their evaluation of the residual resistance was a masterpiece of careful measurement. Using a sensitive galvanometer, they established an upper limit on any remaining resistance, an upper bound that was many orders of magnitude smaller than the resistance of the purest copper at that same temperature. The power of their argument came from the stark, unambiguous nature of the data, which presented a phenomenon that defied the established theoretical models of electrical conduction in metals. Section 3 defining the superconducting state, the critical temperature. Following the initial discovery, the Leiden group's work focused on characterizing the transition itself. This led to the central claim that superconductivity is a distinct state of matter defined by a precise critical temperature, which they denoted subc. Their analysis presented this transition as exceptionally sharp for a pure, strain-free sample like their mercury thread. The internal evidence for this claim came from experiments where they varied the temperature in tiny increments around the transition point, observing that the entire resistance drop occurred within a window of a few hundredths of a Kelvin. This precision was a direct result of their unparalleled control over the helium bath's temperature by manipulating its vapor pressure. The work further extended this concept by examining the effects of material purity. They presented evidence that adding impurities, such as cadmium to the mercury, broadened the transition. This finding was crucial. It supported the argument that superconductivity was an intrinsic property of the ideal, pure material, and that the sharpness of the transition was a key feature of the underlying physics. By evaluating their data, one sees a rigorous program of characterization. They established the critical temperature of mercury at 4.15 Kelvin with a high degree of confidence. The presentation of this sharp, reproducible transition point transformed the phenomenon from a curious anomaly into a definable, thermodynamic state, providing a crucial parameter that any future theory would need to predict. Section 4 the influence of magnetic fields and the critical field. A subsequent and equally profound set of claims involved the interaction of the superconducting state with magnetic fields. The Leiden laboratory reported that the application of a sufficiently strong magnetic field destroyed the superconducting state, restoring the material's normal electrical resistance even at temperatures well below the critical temperature. This established a new parameter for the state, the critical magnetic field, or HSUC. Their experimental reports detailed a systematic mapping of this property. They presented data showing that the critical field was a function of temperature. Its value was highest near absolute zero and decreased smoothly as the temperature rose, reaching zero at the critical temperature itself. This established a phase boundary in a temperamagnetic field diagram, a powerful conceptual tool. An evaluation of their early data suggests the relationship they found was approximately parabolic, a relationship described by the formula h sub of t equals h sub of 0 times the quantity 1 minus the square of the ratio of the temperature to the critical temperature. This empirical formula, while lacking a theoretical basis at the time, was a powerful piece of phenomenological modelling. It demonstrated that superconductivity was a delicate state, its existence governed by both thermal energy and magnetic field energy. The claim was profound. The superconducting state could be switched on and off with a magnetic field, providing another crucial, quantitative puzzle for theorists to solve and opening the door to potential practical applications, however distant they seemed. Section 5 the ubiquity and specificity of the phenomenon. Having characterized the state in mercury, Onnes laboratory embarked on a systematic search for superconductivity in other materials, a program whose results were central to the 1927 understanding. The claims from this survey were both tantalizing and frustrating. They presented definitive evidence that tin and lead also became superconductors, with critical temperatures of 3.7 Kelvin and 7.2 Kelvin, respectively. This demonstrated that superconductivity was a more general phenomenon, a property shared by different elements. Yet, The work also claimed a high degree of specificity. Their experiments or other metals, including a very pure sample of gold and platinum, showed these materials maintained a finite residual resistance down to the lowest temperatures they could achieve, around 1.5 Kelvin. The internal logic of their presentation was to highlight this perplexing selectivity. There appeared to be no simple rule derivable from the periodic table about which elements would superconduct. Good conductors at room temperature, like gold and silver, failed to become superconductors, while a relatively poor conductor like lead exhibited the highest critical temperature found at that time. This set of claims was crucial because it invalidated simple explanations. The phenomenon was clearly a subtle quantum, electronic effect, specific to the detailed atomic and electronic structure of certain metals. This specificity deepened the mystery and provided a complex set of empirical rules for which metals superconduct and at what temperature SAVs serve as a stringent test for any proposed theory. Section 6. The problem of persistent currents and perfect conductivity. Perhaps the most astonishing claim presented by the Leiden school was the existence of persistent currents. To test the reality of absolute zero resistance, they performed an experiment of beautiful simplicity and staggering implication. They induced a current in a closed ring of lead wire cooled below its critical temperature and then removed the external inducing magnet. The central claim was that this current, once established, flowed indefinitely without any measurable decay. In their reports, they described monitoring the magnetic field produced by this current in the ring for extended periods. One famous experiment involved transporting a lead ring with a persistent current from Leiden to a colleague in Cambridge, demonstrating its robustness. The evaluation of this claim depends on the sensitivity of their detection methods. While they could state that the decay was immeasurable, this translates to an upper bound on the material's resistivity, a value they calculated to be less than 10 to the power of -12 times the resistivity of copper. This figure, for all practical purposes, represented zero. The conceptual argument was unassailable. In any circuit with finite resistance, a current must dissipate energy and decay according to Ohm's law. The persistence of the current in the superconducting ring was therefore direct, macroscopic evidence for a state of perfect conductivity. This single experiment provided the most compelling and intuitive proof of the reality of the superconducting state, cementing its status as a phenomenon demanding a fundamental revision of physics. Section 7. Early theoretical speculations and conceptual failures. The final section of the collective Leiden work, as understood circa 1927, concerned the conspicuous absence of a viable theoretical explanation. The reports from Onnes and his successors were models of empirical honesty, detailing the experimental facts with great clarity while acknowledging the profound theoretical impasse. They evaluated and dismissed explanations rooted in classical physics. The Drude model of electrons as a classical gas was entirely inadequate. The claims within this section are about what failed. They argued that any theory based on individual electrons freezing onto atomic lattices was inconsistent with the data. They entertained early quantum ideas, with some speculation that the electrons might form some kind of collective, ordered state, perhaps condensing into a shared quantum, wave function across the entire material, an idea vaguely prefiguring later developments. A certain intellectual wit can be found in the records of the Solvay Conference discussions, where the world's most brilliant minds, including Lorentz, Pauli, and Heisenberg, probed the Leiden data and could offer little more than sophisticated expressions of bafflement. The key claim of this theoretical section was essentially a negative one. No existing framework of electron transport could account for the complete disappearance of resistance or the sharp phase transition. This failure was, in its own way, as important as the experimental successes. It established superconductivity as a premier unsolved problem, a direct challenge to the new quantum mechanics that was then being forged to explain the atom. In conclusion, The body of work on superconductivity consolidated by the ladies schooled in the era surrounding 1927 stands as a paragon of experimental physics. The internal claims, evaluated section by section, reveal a program of extraordinary rigor and systematic discovery, from the engineering triumph of helium liquefaction to the elegant demonstration of persistent currents. The empirical foundations of superconductivity were laid on unshakable ground. The claims regarding the critical temperature, the critical magnetic field, and the specificity of the phenomenon among the elements were presented with a wealth of meticulous data that rendered them incontrovertible. Yet, the ultimate significance of this work, as viewed from that historical moment, resided as much in its theoretical implications as in its experimental findings. By presenting a set of facts so utterly at odds with the classical and early quantum pictures of metallic conduction, Heike Kamerlingh and his laboratory did more than discover a new state of matter. They created a profound and enduring intellectual crisis in condensed matter physics, presenting a perfectly wrapped gift of an experimental mystery, whose resolution would require new concepts of quantum coherence on a macroscopic scale, a solution that would take nearly half a century to arrive. The work's enduring power lies in the absolute integrity of its empirical claims, which served as the irrefutable benchmark against which all future theories would be measured.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.